All right, this presentation is about more vector examples. Okay, so we're going to do some various examples involving vectors. Okay, and components of vectors. So here's the first one. A box is being pulled across the floor by a rope. All right, so let's make a little sketch here. So there's the box on the floor. The rope is at an angle of 30 degrees to the horizontal, and it has a tension of 50 newtons. All right, and what we want to do first is to determine the horizontal component of the force. So I'm going to take this 50 Newton force, which is at an angle, and break it up into components, a horizontal component and a vertical component. All right, and then we're going to first solve for the horizontal component here. All right, now remember the rules for right triangles. We have the sine, cosine, and tangent relationships for a right triangle, the relationship between an angle of the triangle and the sides, okay? That is the non-right angle side, all right? So, and this is summarized in the mnemonic SOHCAHTOA, okay? Where O stands for the opposite side to the angle, A stands for the adjacent or next to side of the angle, S is the sine, C is the cosine, and T is the tangent, and yeah. So in this case, we want to get the horizontal component, which according to the stuff given, 50 newtons is the hypotenuse, and the F sub h, the horizontal component of the force, is the adjacent leg to the angle. So adjacent and hypotenuse are related by the cosine function. So the cosine of 30 is equal to the adjacent over the hypotenuse, the adjacent being force horizontal, and the hypotenuse being 50. So we get this relationship. And my calculator told me that the cosine of 30 is equal to 0.866. Okay, make sure your calculator is in degrees instead of radians, okay, because it needs to be in degrees to give you the proper value. All right, so we need to solve this for F sub h, and that involves multiplying both sides by 50 newtons. And after cancellation, the force horizontal turns out to have a value of 43 newtons. 43.3 if memory serves, so round that to 43 newtons. Part B asks for the vertical component of the force. Now the vertical component is the side opposite to the angle, and opposite and hypotenuse are related by the sine function. So we're going to set up the relationship sine of 30 is equal to opposite over hypotenuse. Substituting the values in, the sine of 30, it turns out to be exactly 1/2. Opposite is force vertical, and hypotenuse is 50. Then multiplying both sides by 50. After cancellation, we get a value for force vertical of 25 newtons. So those are the horizontal and vertical components of the force that is at an angle. Another example we could do involves a plane flying at a bearing of 120 degrees. Now, the navigational compass has 0 degrees as north, 90 degrees as east, 180 degrees as south, and 270 degrees as west. So, where is 120 degrees? Well, it's about, between 90 and 180, a little bit closer to 90, right? So we're going to draw it in like that. And then the angle as measured from 0 being north, bearing 120 degrees. We start at north and go clockwise, okay, 120 degrees. And that leads us to right here. So now I'm going to draw a little vector triangle in here, all right, where the vector has a magnitude of 150 meters per second and this direction. Now remember, this had a bearing of 120 degrees. 120 degrees in our reference navigational compass over here is right around here. And what we need is this little angle right here, okay? And that angle turns out to be 30 degrees, right? Because 120 minus 90, okay, 90 is right there, and then 30 degrees is the leftover. And we need to take this reference angle in order for our calculator to give us the correct value, because the system inside the calculator uses 0 degrees as the positive x-axis, 90 degrees as the positive y-axis. Okay, so not only, but the navigational compass uses 0 degrees as north and 90 degrees as east. So not only are the zeros in a different place, but they increase in opposite directions. The navigational compass increases clockwise. In math class, 0 being here, 90 being here, it increases in the counterclockwise direction. So it's different, okay? But the cosines and sines in our calculators are based on the math system, not the system we're using here. Now, the way to get around that is to use angles only between 0 and 90 degrees. We need to stay in the first quadrant here. We need to have positive values for the cosines and sines. Okay, that's critical. You have to do that. So we're going to use what we call reference angles. Reference angles always being between 0 and 90 degrees. Okay, so in this case it's 30 degrees. We have to do that, otherwise we will not get correct answers. The calculator will give us incorrect answers. Okay, that's just something that we have to compensate for by using this navigational system, which is the one that's used in, if you learn to fly, you'll go to ground school, they call it, and you'll learn this system, okay, or whatever. Ships, submarines, planes, they operate on this system, okay? All right, anyway, so we want the eastward component of the velocity. Now we have a hypotenuse of 150, and the v sub e, the eastward component, is the adjacent side. Okay, adjacent and hypotenuse are related once again by the cosine function. So the cosine of 30 is adjacent over hypotenuse, the v sub e over 150. Okay. Multiply both sides of this equation by 150 so that those cancel out. And the eastward component turns out to be, to the nearest meter per second, 130 meters per second. All right, now we want to determine the southward component. The southward component is opposite the angle. Opposite and hypotenuse are related by the sine function. So the sine of 30 equals opposite over hypotenuse, v sub s over 150. Multiply both sides by 150, and your calculator will give you an answer of 75 meters per second. Okay, so those are the eastward and southward components of the velocity. Next question, how far east has the plane flown after 10 seconds? Okay, well, we can assume that the plane is flying at a constant velocity, so we're going to use d is equal to vt, where t is 10 seconds, d is what we want. Now, what speed do we use? Do we use 150 meters per second? Do we use 130 meters per second? Do we use 75 meters per second? Well, the question is, how far east has the plane flown? Okay, well, how fast is the plane moving to the east? Well, it's moving to the east at 130 meters per second. It's moving at a diagonal of 150, but there's some south stuff going on in there. We want only how fast it's going to the east, and that is 130 meters per second. So if we're asking for the displacement to the east, we need to use the velocity to the east, which is 130 meters per second. Okay? After canceling out the seconds and picking up our calculators, that answer turns out to be about 1,300 meters. All right, so it's important that we use the proper component for the velocity. Got to be careful about that. All right, our final example involves a box on the floor again. Okay, and so what we have is the rope is held at an angle of 40 degrees to the horizontal. Box is a mass of 5 kilograms. 60 newtons is exerted on the rope, and therefore the box. So here's my sketch. I put a little box on the floor and rope at an angle. Okay, there's a tension in the rope of 60 newtons, and it is at an angle of 40 degrees. Okay, and what we want are the horizontal and vertical components. All right, so let's break up this 60 newtons into horizontal and vertical components. And we get this, okay? And we want to find each one in no particular order, just because let's find the horizontal component first. All right, now the horizontal component is the adjacent side to the angle, and adjacent and hypotenuse are once again related by the cosine function. All right, so the cosine of the angle equals f sub h over the hypotenuse of 60 newtons. My calculator told me that the cosine of 40 is equal to 0.766. Then, after multiplying both sides by 60 newtons, all right, that yields an answer of 46 newtons, 46.0 to the nearest tenth of a newton. Okay, so that's the horizontal component. Now let's find the vertical component, the vertical component being the opposite side to the angle. Opposite and hypotenuse are related by the sine function. So sine of 40 is opposite over hypotenuse. Okay, the calculator said sine of 40 is 0.643, and that's equal to force vertical over 60. After multiplying both sides by 60, that yields an answer of 38.6 newtons for the vertical component. Okay. Incidentally, these components do follow the Pythagorean theorem. So if you took f sub h squared plus f sub v squared, that would equal 60 squared. Okay, that might be a little verifier to see if you did your math, if you did your work correctly. Okay, you don't have to, but you can if you want. Now we want to calculate the normal force. And remember, the normal force is the force that the table exerts on the box. Now, up to now, we've said that the normal force is equal to the weight. But that's not going to be the case here. Why? Because there's another vertical force involved, the vertical component of the force on the rope. Okay? In previous examples, if you look back, there were only two vertical forces involved, the weight and the normal force. But there's an additional one here. All right, so it's a little bit more complicated. Now, the weight will be involved, so we can calculate the weight. We need to calculate the weight, which is equal to mg, and we get 49 newtons for the weight. Okay. All right, and now we're going to talk about situations of equilibrium. Okay, which is kind of what we're leading up to in this unit. But a condition of equilibrium is that the forces match in the dimension. Now, in this case, we're talking about the vertical dimension. So the forces up, in order for equilibrium to occur, the forces up have to equal the forces down. All right, and that will be the case. If they didn't match, then the box would either fly up off the table or crash through the table on the way to the floor. Neither of those things happen in this case. So in order for it to be stable in the vertical dimension, the forces up must equal the forces down. Okay, that's a condition of equilibrium. Now, the forces up, there's two of those, the normal force and the vertical component of the force. In the force down, there's only one, the weight. So I can set it up like this. The normal force plus force vertical equals the weight. These are all magnitudes, okay? All right, now I know what the vertical component is and I know what the weight is. So we can substitute those numbers in and then solve for the normal force by subtraction. Okay? And we get a value of 10.4 newtons. Now, intuitively, what that means is the table doesn't have to push with as much force as the weight to hold it up, because the rope is kind of doing some of the effort. You know, the rope is helping out the table to hold the box up. It's helping out the table by 38.6 newtons. So the normal force, the table, does not have to push up with the total force of the weight in order to support it, because the rope is doing some of the job, right? Okay, and then mathematically we can set it up like this to get a value of 10.4 newtons for the normal force. All right, now we want to find the acceleration of the box. Okay, now if given a coefficient of friction, right? So now we're bringing a whole bunch of stuff in here, right? Notice I listed that the normal force is equal to 10.4 newtons now. All right, now if there's an acceleration, that implies a net force is present. Okay, and the net force can be found by ma, right? And then ultimately the acceleration can be found from the net force divided by the mass. Okay, but we don't know what the net force is. The net force is acting in the horizontal, right? What other forces are acting in the horizontal? Well, we have friction acting to the left, but we also have the horizontal component of the force from the rope. Okay, so we have really two forces acting in the horizontal. All right, we have the force of the rope the horizontal component of the force. Now, in previous problems, like in the last unit, this applied force was always parallel to the surface. Not anymore. Now the applied force is at an angle. But we can use SOHCAHTOA to find the component that's parallel to the surface, the horizontal component, and which we have right here. Okay, so now we can go back to previous principles and say, okay, the net force is going to be equal to the vector sum of the horizontal force and the force of friction. Okay. Now we know what the horizontal force is. We don't know what the force of friction is, but we can find it, right, from mu times the normal force. Mu is 0.6, and the normal force, remember, now is 10.4 newtons. Okay. All right, and that friction force then comes out to be 6.24 newtons. Okay. Okay, so now we can start working backwards here. So we have the that should say 6.24. Actually, I don't know why it says that. 6.3. Anyway, so we have a horizontal force of that, a friction force of that. All right. And so the net force then is going to be equal to 39.76 newtons, keeping a whole bunch of digits. That's the net force, which we can finally apply into our Newton's second law equation. And we get that divided by the mass of 5 kilograms. And finally, we arrive at our answer of 8 meters per second squared. Okay. Okay, so this involves a whole bunch of stuff that we've learned throughout the year. We could even, ask how fast, starting from rest, how fast is it going after 5 seconds or whatever. And that would bring the motion equations into it, which we won't do, but we could. So that this problem could involve pretty much all the stuff that we've talked about in this semester so far. All right. So we have some friction going on, we have some net force stuff, we have some Newton's second law, and we have the new complicating factor of the applied force is at an angle. Okay, that's really the only new stuff that we bring in here. But that leads to a whole bunch of different things that we have to consider. The horizontal and vertical component. The normal force is no longer equal to the weight because we have a vertical force, another vertical force involved. Okay, so the normal force is a little bit different. Okay, but from there we can kind of basically do the same kind of stuff to get our answer. All right. So these are just some additional examples that we can do involving vectors and components of vectors. All right. Okay. Now you're in the position of going and trying some practice problems. So have fun with that.